All right, I think it's time. So our next speaker is Lauren Williams, speaking on Grassmannians and Amplituhedra.
So thank you very much. Nice to see everyone again. So in my first two lectures, I discussed the positive Grassmannian. And now in my third lecture, I'm going to introduce an object called the amplituhedron. So let's just recall that the non-negative Grassmannian, or informally the positive Grassmannian, is the subset of the real Grassmannian where the Plücker coordinates are all non-negative. And the amplituhedron, one can think of as a sort of generalization of the positive Grassmannian. Just I'll mention that it was introduced by Arkani-Hamed and Trnka in 2013, and their motivation was to understand scattering amplitudes in n=4 super Yang-Mills theory. So I'm really not going to say anything about the physics. I'll just introduce it as a mathematical object that turns out to be quite interesting. So let's define mat np greater than 0 to be the set of all n by p matrices with maximal minors positive. And in the next definition, I want to fix positive numbers k, n, and m such that k plus m is at most n. And now in order to define the amplituhedron, I need to fix a matrix, a positive matrix in mat n k plus m greater than 0. So Z is going to be an n by k plus m matrix with maximal minors strictly positive. And now the amplituhedron map is a map induced by Z, and it's a map from the non-negative Grassmannian into a related Grassmannian of k-planes and k plus m space. And it's very simple. It's just defined by matrix multiplication. So if I represent my element of the positive Grassmannian by a full rank k by n matrix C, then the map Z tilde is going to take C to the row span of C times Z. So C is a k by n matrix, Z is an n by k plus m matrix. The result is a k by k plus m matrix, which one can check has full rank. And so the row span of the product represents a point in the Grassmannian of k-planes in k plus m space. And so this is the amplituhedron map, and then the amplituhedron, so it depends on these three numbers, n, k, m, and it also depends on our matrix Z. This is a subset of the Grassmannian of k-planes and k plus m space, and it is defined to be the image of the non-negative Grassmannian under the map Z tilde. Okay, so we're just taking all elements in the non-negative Grassmannian. You can represent each one by the row span of a k by n matrix, then you just do the obvious matrix multiplication to get CZ. CZ is a full rank K by K plus M matrix, and its row span represents an element in the Grassmannian of K planes in the K plus M space, and the amplituhedron is just the image of the positive Grassmannian under this map. And of course, as I mentioned before, one needs to verify that CZ has full rank, but this is something that's fairly straightforward to do, and it does follow from the condition that Z is positive and C is positive. Okay, so that's the definition. Any questions about the definition? So then if there's no questions about the definition, I'm going to start by doing a bunch of examples. So, okay, so example 0 is sort of stupid. If K plus M is N, then Z is going to be an invertible square matrix. And so the amplituhedron is just isomorphic to the non-negative Grassmannian. So in this sense, you can think of the amplituhedron as generalizing the totally non-negative Grassmannian. But in general, the map from the non-negative Grassmannian to the amplituhedron drops dimension. Right, the domain has dimension K times N minus K, and on the other hand, the image has dimension K times M, and because we've imposed at the beginning that K plus M is at most N, this map will drop in dimension in general. So the dimension of the amplituhedron is full dimensional inside of the Grassmannian where it lies, but that's less than the dimension of the non-negative Grassmannian. And one more remark is that in general, the amplituhedron, while it lies in the Grassmannian of K planes in K plus M space, it does not lie in the non-negative part. Okay, so now let me do a more interesting example. So let's let K be 1 and M be 2. And then the claim is that the amplituhedron will be a polygon viewed in projective space. So let me explain why this is true. So to see this, let's write our matrix Z. So matrix Z is N by K plus M, which is 3. And let me give names to the row vectors of this N by 3 matrix. And now the fact that Z has maximal minors positive means that the row vectors Zi represent points in P2 in convex position. So if we draw them on the plane, they're arranged like vertices of a polygon. Okay, so this is just from the positivity of Z. And now let's go back and think about what the amplituhedron map does. So the amplituhedron map is going to be a map from the non-negative part of GRKN, which is GR1N, so just projective space, and it lies, the image lies in the Grassmannian of K-planes and K plus M space, which is GR13, which is P2, and recall we're taking a matrix C, which in this case is just a vector, C1 through Cn, and we're mapping it to C times Z. Okay, and the positivity, the non-negativity of flicker coordinates means that all of these CIs are non-negative. Okay, so the amplituhedron map is just this simple matrix multiplication. And now note that if C is this unit vector EI, then CZ is just going to be Z sub I, the ith column of, the ith row of my matrix Z. Okay, so in the image of this map, we do have all of these n points, and so the amplituhedron contains all endpoints, Z1 through Zn, and then for a general C, which is just this non-negative vector, CZ is just going to be a convex combination of those endpoints. And we'll get all points in the interior of this polygon in this way. So therefore, N1, 2 of Z is the n-gon with vertices Z1 through Zn. So it's this whole we sweep out that whole polygon. So this is what happens. This is what happens when K is 1 and M is 2. We get a polygon in P2. And let me slightly generalize this example. So if K is 1 and M is general, then the fact that Z is a positive matrix, in this case, it's an n by 1 plus m matrix, that implies by a old result of Sternfels that the points Zi, so here again I'm thinking of Z as a matrix with row vectors Z1 through Zn. So again, the positivity of the maximal minors implies that the points Zi, viewed as elements of projective space, they are points which have the same combinatorial configuration as the points of a cyclic polytope. And so therefore, by basically the same argument that I gave before, the amplituhedron is a cyclic polytope in projective space. Okay, so this is what happens when we study the amplituhedron with k equals to 1. Now, just a small note, which is that physicists are most interested in the case that m is equal to 4. And so in that case, so our amplituhedron, it lies in grk comma k plus m. And let me just point out that if m is small, then it's desirable to replace this Grassmannian with the isomorphic Grassmannian of m planes in k plus m space. So when m is small, it's sometimes nicer to work with grm comma k plus m instead of the original Grassmannian. Okay, so that motivates what I want to define next, which is a sort of alternate definition of the amplituhedron that we called B amplituhedron. Okay, any questions so far? Okay, so now I want to give a different definition of an amplituhedron-like object. So this was done in a paper with Stephen Karp a few years back. So let's choose Z. Again, it's the same input data as before. It's an n by k plus m matrix with positive maximal minors. And let's let W be the column span of Z. So this is going to be an element of the Grassmannian of k plus m planes in n space. Okay, and now the B amplituhedron is the following object, the n km of Z. And what we're going to do is, for every point, so it's again going to be the image of the non-negative Grassmannian. But now what we're going to do with V is we'll take its orthogonal complement and intersect with W. So W is how we're using the input data of Z. And this space lies in the set of all m-dimensional subspaces of W. So this is my notation for m-dimensional subspaces of W, and W, I'll note, has dimension k plus m. So this, so we've now defined an amplituhedron-like object that lies in a Grassmannian of m planes in k plus m space. Okay, so let me just say a few words to motivate this definition. So why is this a good definition to make? Well, following the original construction, we need a way to combine our input data which was an n by k plus m matrix, and all elements in the non-negative Grassmannian, and we need to combine them to get a bunch of k-dimensional subspaces of a k plus m dimensional vector space. Okay, and now let me just point out that this works because if V lies in the non-negative Grassmannian, then its orthogonal complement lies in Rn, and it has dimension n minus k. And then meanwhile, W, which was the column span of Z, also lies in Rn, and it has dimension k plus m. And so if you now take V perp intersect W, then this will have dimension k plus m plus n minus k minus n, since this is living inside of Rn, so it has the correct dimension m. So all these elements do represent m-dimensional subspaces of W. Okay, so I hope this justifies that this is a reasonable, at least it has, it lies in the expected sort of space. But now I want to further justify this definition by pointing out that it's homeomorphic to the original definition. So okay, so let's choose Z and W as above. And now we define a map from the Grassmannian of M planes in W to the Grassmannian of K planes in K plus M space, sending an M-dimensional subspace to Z of X, where X is a vector in X perp. So Z is a matrix, which one can think of as a linear map from Rn to R to the K plus M. So that's what I mean when I write Z of X here. Okay, and then the statement is that Fz gives a homeomorphism between the B amplituhedron and the original A amplituhedron, taking V perp intersect W to Z tilde of V. Okay, so this is just this is just a way to justify this definition as a reasonable object to look at instead of the A amplituhedron, and particularly nice to look at if M is small. Okay, so now with this new definition, let me give another example. So let's now go to the case where M is as small as possible. Let's think about M equals 1. So then we have Z being a n by k+1 positive matrix. And W is the column span of Z. And this lies in the positive part of the Grassmannian of k+1 planes in n space. And now, what's our definition of the B amplituhedron? Well, this is just the set of all things of the form V perp intersect W, where V ranges over all elements in the non-negative Grassmannian. And this lies inside the Grassmannian of 1 planes in W. So this is just the projectivization of W. Okay, so now let me recall a theorem that I mentioned yesterday. So this was a theorem first written down by Stephen Carpent based on Gantmacher and Krein's work from the 1950s. And it says the following: if we let V be an element of the Grassmannian of k planes in n space, then V lies in the non-negative Grassmannian if and only if the sign variation of all vectors V in capital V is at most k-1. If and only if var bar of W is at least k for all W in the orthogonal complement. And similarly, V lies in the totally positive part if and only if var bar of V is at most k-1. If and only if var of W is at least k for all W in V perp. Okay. So now this characterization is going to be extremely handy for describing elements of this form, because W here lies in a positive Grassmannian, and V perp is in the orthogonal complement of, V perp is the orthogonal complement of a non-negative subspace. So let's see what happens when we apply this theorem. So let's apply this theorem to this space here. For any W in V perp, we're going to, let's see, V is non-negative. And so the statement we want to use here is this one. And that will say that var bar of W is at least k. And for W in capital W, this capital W lies in the positive part of the Grassmannian of k+1 planes in n space. We will have, so here we're going to be using this statement, and this will give us that var bar of W is at most k. And so if W lies in both V perp and W, which is the situation here, we have that var bar of W is exactly equal to K. Okay, so this tells us, that the set of elements in the B amplituhedron all satisfy, they're all vectors with var bar equal to K. Oh, and let me just say verbally, var of a vector was the number of sign flips we see when we ignore the zeros, and var bar was the maximum number of sign flips that we can see if we arbitrarily assign either plus or minus to each zero. Okay, so the upshot is that elements in this B amplituhedron are all vectors with var bar equal to K. And the theorem is that the B amplituhedron, this is for m equals 1, is exactly the set of all vectors in W with var bar equal to K. Okay, so this statement in blue gave us the inclusion. It gave us the inclusion, but now I'm asserting that that inclusion is an equality. Okay, so this is a description of the m equals 1 amplituhedron, and we can also translate that back into a statement about the A amplituhedron as well. Let's see, I'm not going to go into a lot of detail here, but I'll just state the result in a vague way, which is about the combinatorics of this B amplituhedron. And the statement is that we can identify this amplituhedron with the bounded complex of a cyclic hyperplane arrangement. And let me just draw a little picture. I'm going to draw a hyperplane arrangement. And let me label my hyperplanes by H1, H2, H3, H4. This is going to be a picture for B, 4, 2, 1. The number of hyperplanes is this number n. The dimension of the space where it's living is k, which in this case is 2. And m equals 1 because this theorem is exactly about m equals 1. And one can label all the regions of this arrangement by on what side of each hyperplane they're on. And the bounded regions are going to be these sign vectors which see k sign flips. So here k is 2, and so the bounded region of this hyperplane arrangement is like this. And so I'm stating this in a very vague way, so don't worry if you're not following all details, but the upshot is that this B amplituhedron can be identified with this bounded complex of this hyperplane arrangement. And you're seeing in these bounded regions the sign variation. Okay, so now I want to go back a little bit and just talk about what sort of coordinates we should use when we're working with both the A and the B amplituhedron. right? When we talk about Grassmannians, we generally talk about Zucker coordinates. So what should be the coordinates that we use on the amplituhedron? Okay, so first I'm going to talk about the original amplituhedron. So let's let Z again be written as a matrix where I give a notation Z1 through Zn for its rows. And now, given a matrix Y, so let's say that Y is a K by K plus M matrix. And I'll think of this as before. I will sometimes identify matrices with their row span. So I'm going to think of this matrix as a K-plane in K plus M space. And given positive numbers I1 through I sub m, which are all elements of the numbers of the set 1 through n.
Lauren?
Yes?
There's a question in the chat by Martin Reading. Is there a fixed object which is the cyclic arrangement with n hyperplanes in Rk? Or are we talking about a hyperplane arrangement that has the property of being?
Oh yeah, thank you for the question. So I'm using it a little bit loosely in the sense that when I talk about cyclic polytope, I'm just thinking of something that combinatorially has the structure of a cyclic polytope. So I'm not requiring anything like precise moment curve, but in this case, when I say cyclic hyperplane arrangement, these are going to be hyperplanes that I read off from W after choosing a basis for W. So anyway, so I'm not talking about a sort of the cyclic hyperplane arrangement, but I'm being a little bit general, I guess, in my usage of the term cyclic hyperplane arrangement. Okay, so now talking about coordinates on the amplituhedron. So given y in this Grassmannian, and given m numbers from 1 through n, we will define the twistor coordinate as follows. So we'll denote it as y zi1 ... zim, and this is going to be defined to be the determinant of the matrix I get if I put the matrix Y on top, and then I put columns zi1, rows zi1 through zim below. Okay, so Y is a K by K plus M matrix. And so when I take this matrix and I add M row vectors, which are all vectors in K plus M, I get a square matrix, so I can take its determinant. And so this is called twistor coordinate. And if sometimes I will abbreviate things, and if I is taken to be a list of numbers written in order, then we also abbreviate this as just y z sub I. Okay, so so these are coordinates that we can look at on elements of this Grassmannian of K-planes and K plus M space. And these, I believe, first appeared in a paper of Arkani-Hamed, Hugh Thomas, and Trnka. Okay, so these are coordinates on the amplituhedron, on the original amplituhedron, which is a subset of K-planes and K plus M space. But now, now that we have this definition of B amplituhedron, we can think about what these translate into on the B amplituhedron. And the lemma is that these twistor coordinates on the original amplituhedron are just exactly the Plücker coordinates on the B amplituhedron. And concretely, if x lies in the B amplituhedron, which is contained in the set of all K-planes in W, which in turn is contained in the set of K-planes in Rn. And if you apply this map I wrote down earlier, mapping points in the B amplituhedron to the A amplituhedron, then the ith Plücker coordinate on x is exactly the ith twistor coordinate on y. Okay. Okay, so anyway, so we have these natural coordinates for talking about the A amplituhedron, and they translate into Plücker coordinates on the B amplituhedron. Okay, so so recall I defined the amplituhedron as a oh, sorry, I realize I have a typo here. This should be no, that's fine. K plus and K plus M space. Okay, so given that we defined the amplituhedron in this sort of weird or confusing way, we defined the amplituhedron as the image of the positive Grassmannian under this map Z tilde. That's not a very, very explicit definition. And we know that the amplituhedron lies inside of this Grassmannian. So a natural question is, how can you describe the amplituhedron concretely inside of this Grassmannian? Right? We don't want to just describe it as the image of all these points under a map. We'd rather describe it concretely inside of this Grassmannian. So question is, given that the amplituhedron lies inside here, how can we directly describe it over here? Okay, so this is not understood in general, but I can tell you what's true for, well, okay, for m equals 1, we understand everything. And for m equals 2, the following was conjectured by Arkani-Hamed and Hugh Thomas and Trnka. And we proved this with Matteo Parisi and Melissa Sherman-Bennett. Okay, so let's fix Z. This is our input data as always. M is 2 here, so this is a n by k plus 2 matrix. And now let's let f n k2 of Z be the set of all points in the Grassmannian of k-planes in k plus 2 space, and such that the twistor coordinate y, zi, zi plus 1 is greater than 0 for all I. And also I want to consider what happens when I look at Zn, Z1. Okay, so I have these fixed twistor coordinates which are required to be 0, and moreover I have a sign variation condition, which is that if I look at y, z1, z2, y, z1, z3, and y, z1, zn, the sign variation here, the number of sign flips I see as I read these coordinates left to right, must be k. Okay, so this is just the definition of this set F, and the statement is that the amplituhedron is equal to the closure of this set. Okay, and just a small remark about this statement. So basically I think of this as a sign variation way to cut out points in the amplituhedron inside of the ambient Grassmannian where it lives. But just to make a few historical remarks, one of these inclusions is fairly straightforward. This one was verified by Arkani-Hamed and Trnka, and separately in our paper with Stephen Karp, and but it's the hard direction is this one. Okay, I think my time is up. Is that right?
Yes.
Okay, all right, then I will stop there.
Thank you. Let's thank the speaker. Any questions or comments?
I have a question, but I don't know if Lauren can hear me.
If you speak up
I have to
a
shout.
little bit, maybe. That's right.
Can you hear me now, Lauren?
Sort of.
Okay, I'll try and shout even louder. Is it possible to describe where the positroid cells go under the map from the positive Grassmannian to the amplituhedron?
Yeah, so that's a great question, where the positroid cells go on under the amplituhedron map. So for an arbitrary positroid cell, an arbitrary amplituhedron map, it's not well understood. Now, what we did in order to understand, in order to prove this theorem, what we did was so a big step here was to find 2k dimensional positroid cells of the non-negative Grassmannian such that Z tilde is injective on them. So right, so in this case, Z tilde maps from the non-negative Grassmannian onto this amplituhedron contained in GR k, k plus 2, which has dimension 2k. And so the upshot of proving this theorem was to find a whole bunch of 2k dimensional cells over here on which Z tilde is injective, and to show and to find, moreover, special collections of these two k-dimensional cells whose images cover the amplituhedron, and to also describe their images under the map. So basically, to answer your question, in some nice cases, and in here, in this particular example, we could describe concretely the images of certain 2 k-dimensional cells. But in general, it's a little bit tricky to understand exactly what's the image of any cell. Yeah, does that answer the question?
Yep, thanks.
The question by Greg Massacre. I don't know whether I should read this or.
Oh, okay, yes, I can see it. Great, so the question is, if we change the definition of F and K2 and look at Z2, Z1, Z2, Z3, and so on. Yes, that's a great question, and we can definitely do that. We can. There's nothing terribly special about this one here. We can replace it with I, and then I think what we want to do is look at Zi plus 1, and then Zi plus 2, and then sort of wrap around Zi, Zn, Zi, Z1, and so on. So yes, so there's nothing special about that one, and you can replace it basically with I, and you get the same statement.
Any further questions or remarks?
To follow up on Greg's, what happens if you use the endpoints of edges in any triangulation of the n-gon? You explained the fan triangulations.
Oh, yes, yes. Yes. So, right. So you're, so I don't know what to do. I don't know how to replace this statement with an analog for an arbitrary triangulation, because this statement involves a lot on having a sort of canonical order of the triangles in your triangulation.
Right, yes, okay.
So just to say, it's possible one can do it, but it's not totally obvious to me what should be the statement. Yeah, thank you.
Any other questions or remarks? That doesn't seem to be the case, so let's thank Lauren and all the speakers of today's session.
Thank you.
We'll resume again tomorrow at 1 p.m. UK time.